Well, hello C++ programmers. Brian Malloy here, and today I want to introduce the topic of inheritance. And you may have heard of inheritance or even used inheritance in a different language. I want to specifically talk about inheritance in C++. Not because it's drastically different from other languages, but because it is different, at least syntactically, but also semantically. So what I have right here in front of you is a kind of vanilla example of inheritance. I could have used, I have some other examples that I'll use in later videos in talking about inheritance, but I wanted one that was vanilla because I wanted to abstract the ideas I want to present, A, and B, if we have a meaningful example, sometimes it's hard to get meaningful functions. So let me see if I can explain what I mean. So here I have a base class, A, and here I have a derived class, B. Now, how do I know that B is derived from A? It's the colon public A. So this is an example of public inheritance. You can have private inheritance, virtual public inheritance, all kinds of versions. In my discussions in these videos, I'll probably stick pretty much with straight public inheritance. Private inheritance has been used. There's a gentleman in France who talks about a marriage of convenience where he uses public and private inheritance. And that's all an interesting topic that we may broach in later videos. But today I just want us to talk about straightforward public inheritance. B publicly inherits from A. And the other thing I want to say about inheritance is that it is a unit of reuse. It's a construct built into object-oriented languages to provide reuse. So what do I mean by that? Well, this isn't such a good example to explain what inheritance is good for, and we'll come to that in later videos, but at least it shows inheritance. So what am I saying here? So I have up here in base class A, I have a name. So class A has a name. And it has, generally we would provide functions that, that operate on a name, like get name and set name, possibly. And so what do I get if I derive a class from A? Well, I get pretty much everything in A. So B is an A. And that is the key idea with inheritance. The is a relationship. In later videos, I'll show you some diagrams, some UML diagrams of inheritance, and the arrow points from B to A in the inheritance tree because B is an A. And that is an idea also that I'd like to explore in subsequent videos. But today I just want to talk mostly syntax and semantics of the three kinds of functions that you can have in a base class. And that's why I've chosen this kind of vanilla A-B example, because I can just throw them up here and show them to you, and I don't have to say the reason this is that, although I do want to talk about what it means. So let's get right to it. So I have a constructor. Okay, the normal constructor, and I'm using an initialization list to take the parameter and assign it to my data attribute name. So here's an initialization list, and I've talked about these in previous videos, and I've even shown that they are more efficient in some cases in previous videos. And if you don't remember that, you might want to go back and review that. When it comes to inheritance, initialization lists become a sine qua non. What I mean by that is you need an initialization list, and I'll talk about it down here, to initialize. So, there's no other way to do it, but I'll come back to that. Okay, here I have a destructor that does nothing, but I stuck it in here because I want to show you something about destructors. I don't know if I'll get to it in this video, but there is a sneaky little issue with regard to destructors in base classes that they need to be virtual. If they are not virtual, hopefully you'll get a warning, at least in most cases, and in other cases you could have a memory leak in the derived class. So we'll get to that in a later video, most likely. Here I have a function that looks weird. Okay, why does it look weird? Well, it may not look weird, but let me just point out the syntax of this function called print on line 9. Okay, so it's the return type of print is void, which means it's not going to return anything. Okay, nothing new there. It is a virtual function. Okay, now virtual has a very special meaning in C++, and in C++ you can designate some functions as virtual and other functions as not virtual. And we've done that right down here. This is a non-virtual function. This is non-virtual. This function is virtual, but it goes beyond virtual. It is pure virtual. What do I mean by pure virtual? There's this strange syntax equals 0. And don't try to convince yourself that it means you're assigning some value to this function, its return type, or whatever. This is simply syntax to indicate that this is a pure virtual function. Now, that may sound like it's not a big deal, but it's a huge deal, because by virtue of the fact, and I don't mean to make a pun here, but by virtue of the fact that it is a pure virtual function, that fact alone makes class A an abstract class, and in this case an abstract base class. What does that mean? If it's an abstract base class, that is, if it has a pure virtual function in it, that means that you cannot instantiate class A. All right, let me show you the three functions and then I'll prove that to you. Okay, so I have a pure virtual function, a virtual function, and a non-virtual function. So let me show you that you cannot instantiate A. And then after I show you that, I'd like to talk about the semantics of these three kinds of functions. Okay, let me just put comments after each of these so we can remember that. So this is a pure virtual function. Let's see, this one, where can I put this? Do something. This is a, let's put it right here. This is a virtual function. And this function is I should have left that there, a non-virtual function. Okay, so there are the three types. All right, we have pure virtual, virtual, and non-virtual. So let's leave those comments in there just to remind us that those are the three types of functions that you can have in a base class in an inheritance hierarchy. All right, the next thing I want to do is show you that I cannot instantiate A. So I'll just do that by doing something like A. All right, and I hope I get an error on line 29. So let me just see, I do make, and we see that. What does it say? It says error, variable type A is an abstract class. Okay, it's abstract. Note, unimplemented pure virtual method in A. Okay, so this is a pure virtual method. All right, so the compiler, the C++ compiler that I'm using, what am I using here? I'm using Clang. But both compilers, G++ and Clang++, the two compilers that I use, are going to tell you the same thing. Excuse me. Namely that I cannot instantiate A. And you might say, well, I didn't make it a pointer. Let me make it a pointer. It doesn't change the fact. Equals new A does not change the fact that I cannot instantiate class A. So let me try it again. I'll clear the screen, try to do it. Allocated an abstract, same thing. We have a pure virtual method, print. Okay, so I cannot instantiate class A. No can do. Why? Because I have a pure virtual method. That's the message from the compiler right here. Pure virtual method. Okay, so pure virtual method may seem like not a big deal, but it is. It is a huge deal in terms of the identity of the class, because it designates this class now as an abstract base class. Now, it means I can't instantiate. Now, you might be saying, well, what good is it? Well, it has lots of good. And we'll talk about that in a later video, because abstract base classes define an interface that all derived classes must have. What I mean by that is I can't instantiate B either if I don't provide an implementation for the pure virtual function. So what I have down here is A star X is equal to a new B. And I want to talk about this especially in later videos. Namely that the type of X is A star, but the type of object that X points to is a B. And that is the groundwork for polymorphism, which I want to talk about. And it is a very important concept in object-oriented programming, object technology, and in programming in C++. We'll come back to that one though. So let me come back here to what if I don't provide an implementation of print. Well, let me show you that this will compile and run right now. Okay, so I'll compile. Whoops. Did I leave that in here? I probably did not save it. Let me save this. So what am I doing here? I have an abstract base class A with three functions, and then I have a B. that currently provides an implementation for print and doesn't do much else. I have a constructor. Let's just talk about B a little bit here. So this constructor, has no data attributes. Why I didn't give it any? I just wanted to keep it so vanilla. So no data attributes of itself. But of course it must accept a parameter that it can pass to the base class to initialize it. So when I instantiate B here, I provide a string for the name of the dragon that the player has to kill at Kynes Grove in a video game called Skyrim by Bethesda. Sorry to make the plug. Okay, so I pass this string into the constructor for B, and then I use an initialization list, and this is the only way I can pass this parameter to the base class is using an initialization list. So one of the things you see here is that initialization lists are not just for efficiency. Syntactically, it's the only way I can pass this parameter n to this base class A. Okay, so I'm going to next, the first thing I do in my initialization list here, and now you can hear my clock is going to announce that it is 9 a.m. I apologize. And while it's ringing, I'm going to sip some coffee. So I pass n, I'm going to talk over it, up to this base class, okay? And then I have this print, and all print does is calls function up here and get name. So one of the things I'm trying to show you here is a way that I can call a function in a base class. Now, frankly, I don't need this. So let me show you that this compiles now and runs. I don't need this a : because it's not static or anything, and this will still work. Okay, but I just wanted to show you that if you want to specifically call a function, and if I had a get name here and I wanted to distinguish this get name from that get name, I could do it with the scope operator. Okay, I've shown you that this program compiles and executes. Now let me try this. I'm going to comment this out. Of course I can't call it, but that's okay. Now what I want to show you is that this will not compile. Why will it not compile? Let me just get rid of it. Okay, it's not even there. I'll get rid of this one too, so you don't even see it. Okay, so what am I saying? What I'm saying here is that this program will not compile. Why will it not compile? Because I have a pure virtual function here, and I don't provide an implementation in the derived class. And that is the key virtue of a pure virtual function. What is that key virtue? It is namely that if you have a pure virtual function in the base class, if you create an instance of a derived class, you can be guaranteed that these pure virtual functions here must be implemented in the derived class. And what that does is that opens up a whole new vista of programming techniques where we program to an interface, not an implementation. Now, so let me make sure I've saved it, and let me, try to compile it, and it says error. Thank you, Spock. Allocating an object of abstract class type B. And what's wrong with that? Okay, so the error is I'm trying to instantiate B. Why is that an error? Because I have an unimplemented pure virtual method print. So, in other words, if I have a pure virtual method, I am defining an interface that every derived class must have. So, for example, in video games, one of the frequent things we do in video games is we update our objects and we draw them. We draw and update, draw, update, draw, update, draw, update. We do all of those things. So what that means is that I can have an abstract base class with pure virtual methods draw and update, and every class derived from that base class must implement draw and must implement update. Therefore, I can program to that interface, knowing full well that those functions must be resident in the derived class. Okay, so let me put this back to what we had. Okay, I'm almost finished with this introductory video. So let me just talk about the semantics of these. So let's start with the non-virtual function. A non-virtual function is typically a function that manipulates the data in the class in which it appears. So This is a get name. What does get name do? It manipulates the data attributes of A, where I find it. So it's non-virtual. And what it means is that I shouldn't override this. Why would I want to override get name? Why would I want to provide a get name here? It doesn't mean that I may not. It means I should not. Okay, so if I have a get name down here, what would it do? I mean, I assume it would call the get name up here because we don't have a name here. The name is in A, and we've derived B from A so that we can reuse this data attribute. Why would I want to override this? Okay, so that's the semantics, the meaning of non-virtual functions. Non-virtual functions in a base class manipulate, access the data attributes of the class, and we shouldn't override them. May we? Yes. In fact, it could be that for some reason in some derived class I want to override it, so I actually could. But we probably shouldn't. And in fact, if we find ourselves overriding it, maybe our design needs some work. Okay, here is a pure virtual function. A pure virtual function says that I may override this. Okay, so should not, may, and must. Those are the semantics of these three functions. A non-virtual function should not be overridden. A virtual function may be overridden. That is, I can accept this implementation as what I want, or I can override it and do something else. So it's called do something. I may want to do something in B, but I may want to also derive a class C from A and do something else. So I can override this in that class if I want. Pure virtual function means I must override it in the derived class. And I've tried to demonstrate that to you. If I don't override it in the derived class, I can't instantiate B either. So those are the semantics of these three functions. Non-virtual means I should not override. Virtual means I may override. Pure virtual means I must override. So that is a summary and a description of the three kinds of functions that you can have in the base class, and we will talk more about inheritance in subsequent videos, culminating hopefully in a discussion of polymorphism. So Brian Malloy, over and out. Happy programming.